So a bonding pair, right? A bonding pair is a pair of electrons, a pair of electrons that are shared between two atoms, or between atoms in a covalent bond. That should be okay then. Is it okay with us?
Yes, sir.
Alright. Then now they need the Lewis structures for those molecules. So just as we remind ourselves, how many valence electrons does nitrogen have?
I think it's five, sir.
Okay, so we shall say 1, 2, 3, 4, 5. And then the NH3 there you show with H. Now because it's a Lewis structure, you're not supposed to be showing lines here. You're supposed to show the atoms straight. You understand?
Yes, sir.
And then HOCl, how do we draw that one?
Mm, so can I look at it for a bit and then I'll tell you?
No problem.
So I can't see using Cl to be our central atom.
Cl.
Yes, can we try it that way?
But Cl has 7 valence electrons, right?
Yes, sir.
So let's see. But then let's see. Cl 1, 2, 3, 4, 5, 6, 7. Yeah, we've made it the central atom. What's next now?
So I think oxygen was supposed to be the central atom, not Cl. Now that I look at it.
Okay, let's make oxygen the central atom. So there we have
And then so we can bring the hydrogen there at the oxygen.
then we have hydrogen.
Yes, sir.
Is this okay?
Yes, sir. Is it correct or
Yes, it's correct. That's correct there. That's how you draw the Lewis structure for um hypochlorous acid. Hypochlorous acid, which is HOCl. Okay, now what are the number of bonding pairs in the NH3?
within the NH3? Don't we have three of them, sir?
Okay, 3 bonding pairs, right? 3 bonding pairs. Yeah, that's correct. And lone pairs in the number of lone pairs on the oxygen atom in the hypochlorous acid. Lone pairs.
Also, wait. No, no, no. Two, two.
Two lone pairs.
Yes, sir.
Yes, correct. So that would be two lone pairs, of which is this one and that one. You agree?
Yes, sir. Yes, sir.
All right. And then what is the shape of the ammonia molecule?
So, sir, it's the NH3, right?
Mm-hmm.
Okay. Isn't it the trigonal pyramidal?
Yes, that's a trigonal pyramidal. That's a trigonal pyramidal, and as you can remember that it has three bond pairs and one lone pair. It's a non-ideal shape, so that makes it a polar molecule. Right. So which bond, NH or OH, is more polar? And then give a reason for your answer. Which one is more polar?
So, about this one, I'm not quite too sure. I don't want to lie. I'm not quite too sure.
Um, Remember that in terms of whenever atoms, right, have a different electronegativity, we say that they, if you have a bond, right, if you have a bond between atoms of the same element, that means that they have the same electronegativity. So it's like a purely non-polar molecule.
So,
But
there's an even distribution of charge.
yes, there is an even distribution of charge. But then if it happens that you have one of the atoms having a different electronegativity from the other, then now it's gonna be polar, because there will be a side that is slightly positive and a side that will be slightly negative due to the unequal distribution of charge. Are we together?
Yes, sir.
Yeah, so to answer this question in simple words, we need to calculate the electronegativity difference, because electronegativity of nitrogen is not the same as hydrogen, and of oxygen is not the same as hydrogen. So if we calculate um, En difference for NH, it's gonna be equal to um, 3 minus 2 comma 1.
Comma.
Is
Oh,
a
3,1.
mm, no, 3 minus
Are you
2
talking
comma
about
1.
NH?
Yeah, NH, which is 0 comma 9, right?
Yes, sir.
And then if we check the electronegativity difference for OH, I believe the higher one should be 3 comma 5, then minus the 2 comma 1, and then you should get 1 comma 4, ne? So therefore the OH bond is more polar, because there is a higher electronegativity difference. Is it clear?
Also, within this type of question, I need to calculate the electronegativity difference first, and then I can see which one is the biggest. Then I can say that the one that's the biggest is more polar.
Yes, yes.
Okay. Thank you, sir.
Is it clear?
Yes, sir.
Okay. So indeed, you need to check the electronegativity difference for NH and then for OH. The one that will be higher, then that will be more polar. Then
No polar.
right, and then now write down the type of intermolecular forces present in both ammonia and hypochlorous hypochlorous acid. In both of them, they have the same type of intermolecular forces. So when you look at NH3, when you look at hypochlorous acid, they have the same intermolecular forces present. So which ones, what type of intermolecular forces are present in both?
So on these hydrogen bonds,
Hydrogen bonds. Are you sure it's hydrogen bonds?
no, sir, I'm still.
Mm-hmm. Okay, still nothing
So I think it's a dipole, dipole.
in both of them. Well, ammonia. Um, ammonia. It is a trigonal pyramidal, like we said. It's a trigonal. It has a trigonal pyramidal shape, right? Which makes it a polar molecule. And our HOCl, it has two bond pairs and two lone pairs. Now, if you remember our table of shapes, if you have two bond pairs and two lone pairs,
This is angular or bent.
that's angular or bent. So it means this is also, so this is angular or bent. So which means this is also a polar molecule. So it means inside of HOCl there's gonna be dipole forces, and then in NH3 there will be dipole forces, because we're looking at two NH3 molecules, right? So since this is polar, the intermolecular forces will be dipole, and when you're checking HOCl, um, Cl, both of them, if you have both, because both will be polar, that will be dipole forces. But they have a special type of dipole forces. So both of them have what you call hydrogen bonds. Hydrogen bonds are a special type of dipole. When you have hydrogen bonded to north, hydrogen bonded to north, meaning to nitrogen, oxygen, and fluorine. So we can see here there is hydrogen bonded to nitrogen, so it's a hydrogen bond, and then here we have hydrogen bonded to oxygen, so it means there are hydrogen bonds there. So we need to remember that um, whenever we have such a case, we're going to have hydrogen bonds. Is it clear?
Yes, sir.
Now, speaking of which, right? Remember that the strength of the intermolecular forces goes like this. The strongest of them all is what?
Hydrogen. Hydrogen bonds. Sorry, sir.
Hmm. Can I ask you something?
Yes, sir.
In your school, when you were being taught, which intermolecular force they say are the strongest?
So isn't it the hydrogen bonds?
No, like I'm asking as to whether at your school, like, did they um say that, or perhaps maybe you heard it from me. So I just wanna hear this, the distinction there.
So I heard it from you, not from like at school.
Okay. Um, I think I have a confession to make. And you need to grab some wine for this thing. No, like, don't drink wine. I'm just saying. I yeah. The thing is, there was a bit of a mix-up, and I only realized it over the past um few lessons I was having with my other grade 11s. So actually, the list goes like this, ne? Ion, um, ion dipole forces are the strongest. Then number two, it's ion induced dipole. It's ion induced dipole forces. And then number three is hydrogen bonds. Is hydrogen bonds. Now I'm going to explain why that is the case. And then number four is gonna be um, dipole forces. Number five becomes dipole induced dipole, right? Dipole induced dipole forces. And then you have London forces, of which London forces is induced dipole forces. Is induced dipole forces, also known as induced dipole, ne? Induced dipole, and then induced dipole. Basically, it's a intermolecular force between two non-polar. Here it's a polar and a non-polar. Here it's a polar and a polar. Now, these ones from hydrogen bonds, ne? They are called van der Waals forces. Van der Waals forces, ne? They are called van der Waals forces. So they are at the bottom, meaning they are weaker as compared to any forces that are going to have an ionic compound. When you talk about ion, we're talking about a metal and a non-metal. For example, sodium chloride has ion forces, right, between the molecules. If you put sodium chloride in water, meaning if you have NaCl in aqueous solution, this means you are talking about NaCl in water. Okay, this will be NaCl and water. Now the forces between them is gonna be ion dipole forces. Then if you take NaCl, you put it in, let's say, in oxygen, right? Then there what you have is an ion, and then it's a non-polar molecule. So that means that you are dealing with an ion induced dipole. So here's the thing: hydrogen bonds, ne, are still dipole forces. If you can remember from the list I once gave you, I put hydrogen bonds at the start, then after that I came to ion dipole, ion induced, right? I'm hoping I did put those. I think induced I didn't put it at that time. So I had hydrogen, then we had ion dipole, then we had dipole. So here's the thing: um because ion dipole forces were already on top of the list when you compare them with dipole, it tells you that they are stronger than hydrogen, because hydrogen bonds are still dipole, just that it's a special dipole force. So Uh, in simple words, what I'm trying to say is that the list goes as follows: the strongest is ion dipole, and then followed by ion induced, and then number three it's going to be hydrogen bonds, then dipole dipole, and then dipole induced, and then London forces. And then from hydrogen bonds to London forces, they're called van der Waals forces. So sometimes they like to say, give us the van der Waals forces in HCl. You have to understand that they want you to tell us, um, is HCl, is the forces between HCl molecules, is it dipole dipole, it's what, you see. So please, from this moment, please remember that hydrogen bonds is like number three, then followed by dipole dipole, dipole induced, and then London forces. Is it clear? Did I lose you somewhere?
Well, it was glitching somewhere. There was
Mm.
a point where you were quiet.
Okay. Okay, but what I was saying is that please just remember that ion dipole, ion induced, they are the top two, then followed by van der Waals forces. Of which van der Waals forces, the top one will be hydrogen bonds because they are a special type of dipole dipole force.
Okay, sir.
Yes, yes. So please make sure you remember that, especially when you have to deal with melting point and boiling point. It's quite important that if you are dealing with sodium chloride, especially this one, sodium chloride, and maybe you might be dealing with water, you have to understand that sodium chloride is going to have a high melting point as compared to water. I mean, think of it. You can take a cup of salt, ne, and put that cup of salt in a pan or in a pot. Then take a cup of water and put it also in a pot or in a pan. In a pan. If you heat those things, the one that is going to heat up first or boil first is the water. But the salt, imagine the salt has to turn from solid first to liquid. Then after turning into liquid, it has to boil. It's gonna take an enormous amount of energy to do that. So that's why salt is gonna have a high boiling point as compared to water. So in that case, it reminds us that ionic compounds have stronger intermolecular forces as compared to just polar molecules. You see, so whenever it's ion dipole or ion induced, it's gonna be having a higher boiling point compared to the ones that have van der Waals forces. Are we clear now? Um, yeah, hope that is fine. Hope that is fine. Eh, this was a question that was just also there, just that it couldn't fit on the screen. But
Can you please repeat what you said again? Because it's doing the same thing that it just did.
no, we'll just explain.
Sir?
All right, but did you get the list in terms of the order?
Yes, sir.
Yeah, that's just it. That's just it. Nothing more, nothing less. Just knowing that ion dipole are stronger as compared to hydrogen bonds, dipole, dipole, and the rest. So now, when ammonia dissolves in water, right, the ammonium ion is formed. What type of bond forms between the ammonia molecule and the hydrogen ion? What type of intermolecular forces are those? What type of bond is that? Oh yeah, so that is dative covalent bond, eh? Dative covalent bond. And remember that dative covalent bond is gonna exist for NH4 plus, and then also for the hydronium ion, which is H3O plus. And sometimes they'll ask you to show the formation. How you do that is to show the intermolecular forces here. I mean, to show the valence electrons for nitrogen. Sorry, and then plus, um, no, for NH3, sorry, for NH3. Okay, so this is NH3. Then it's gonna react with the H plus proton, which means the hydrogen that has lost an electron, then they will form. So you will draw this again. Oh my goodness, yeah. You draw that again, and then you put it there. Then you will put the hydrogen at the top there on the lone pair, and then you do not forget to show that it's gonna have a plus there. So this is how you can show the formation of a dative covalent bond, right? And then also asked to show for H3O plus the dative covalent bond for H3O plus. So this one was for NH4 NH4 plus. For H3O plus, you would say, you would show oxygen, right? Oxygen, and then it's gonna react with the H plus, and then what it will form there is a dative covalent bond. So you'll have something like this, and then you show that the hydrogen is gonna come here, and because it's there, the whole molecule now is gonna be plus. Okay, so that is to show that you have H2O bonding with the H plus, it forms H3O plus. So that is the dative covalent bond of hydronium ion there. Right, so that's what we have. And then from there, I believe it's just to remember also how to explain your the in terms of the bond energy, the graphs. I think um we have those, but I also wanted us to look at this melting point and boiling point revision, right? So here we go. Are you able to see that?
Yes, sir.
Right, so we have some substance. Remember, you need to remember your definitions, right? For melting point, you need to remember the definition for boiling point also, and then for vapor pressure. Now the yeah, by the way, what is melting point?
So isn't it the temperature at which a solid becomes a liquid while it is given like enough heat?
mm, okay, if that is the one given at school, we probably need to stick by it, but is a temperature at which the solid and liquid phase of a substance are at equilibrium. But if that is the one you're given there, because grade 11 is a bit tricky, because I don't know, some teachers still prefer definitions that are not on the exam guideline, of which I don't understand why, but yeah. Okay, so here we need the difference in melting point of HF and HCl by referring to the type of intermolecular forces. So take a minute to analyze that table, and then could you account for that difference in melting point between HF and HCl? by referring to the type of intermolecular forces for 4 marks. Any idea?
So I'm still looking through it.
Okay.
So within this one, can you please assist? I'm not quite too sure on what to answer.
Um, what intermolecular forces would you say are in HF? In HF. In these questions, you need to check the intermolecular forces in each of the molecules that they are talking about in order for you to answer it correctly. So, HF, like we said, whenever H is bonded to NOF, nitrogen, oxygen, or fluorine, then we're gonna have hydrogen bonds. So in HF we have hydrogen bonds, and then in HCl we have simply dipole forces. We have dipole forces, of which is because HCl is a polar molecule. It's it's a polar molecule. Remember, linear molecules, as long as the atoms are not the same, it becomes a polar. But if the atoms are of different elements, then it becomes a polar molecule. So, for example, if I have F and F, it's non-polar. But if I have H, F, it becomes a polar, right? It becomes a polar. But it's just that this one is a special type of dipole. Dipole is called hydrogen bond. But if you have HCl, it's gonna be simply a polar molecule. So hence you'll have dipole forces. And then now you'll then tell them that remember it's 4 marks. So you need to first of all identify the intermolecular forces in each substance. You identify the intermolecular force. That's always the first step. You never have to idle or think hard about what you need to first start doing. If you're comparing two molecules, the first thing to always do is to identify the intermolecular forces in each of the molecules. And then after that, you talk about the energy and the strength of those intermolecular forces. Then you talk about the energy, and then you conclude. ESEC. Then you conclude. So I've already identified the type of intermolecular forces. Then we know that hydrogen bonds are stronger than dipole because on the list of van der Waals forces, hydrogen bond is the one that is starting. So hydrogen bonds are stronger than dipole forces. Right, dipole forces. So that means that more energy will be required to overcome intermolecular forces. More energy will be required will be required to overcome intermolecular forces in HF compared to HCl. And because of that, your conclusion will now be hence HF is going to have a higher boiling point and a melting point. So hence HF will have a higher boiling point and also melting point. So you can see there, you negative 83 is bigger than negative 114. We can't say negative 114 is bigger than negative 83. Mathematically, negative 83 is bigger than negative 114. So hence this one has a higher melting point, and also it has a higher boiling point, as you can see, compared to HCl. But remember, the one with the higher boiling point and melting point is gonna have the lowest vapor pressure. Then 3.3, which one of the substances above A, B, C, or D is a liquid at 25 degrees Celsius? Which one would you say is a liquid at 25 degrees Celsius? There, right, there you need to check the boiling point. Or in fact, you need to check the, you need to check the melting point and then the boiling point. So these are quite tricky questions there, especially this one. There you need to be careful. So now, the boiling point of this one is 19,54, which means above 19,54, A is gonna be a gas. You understand? Above this value, A is gonna be a gas. Now we're talking about 25. 25 is above 19,54, which means HF at 25 degrees is already a gas. So this one is out, right? Then we check HCF. HCF becomes a gas at negative 81,7. Please understand that a melting point is a temperature whereby that substance is going to be changing from solid to liquid. So which means above the melting point, the substance is a liquid, right? So for example, this one becomes a liquid at around negative 114,2 degrees Celsius. And once it's liquid, once the temperature reaches negative 81,7, it changes to gas. So the boiling point tells us the temperature at which the substance will become a gas. So this one at around 25 degrees Celsius, it's already a gas. So it's out, right? It's out. Then let's check the last one. The last one there, the boiling point is negative 78. So this is the temperature at which it changes to become a gas, which is a very low temperature. At 25, it's still a gas. But this one, the boiling point is 46, which means the temperature at which it's gonna become a gas is 46, which means below 46, it's a liquid, and then below negative 115, it's a solid. So between negative 115 and 46, it's a liquid. So that is the one there. So the answer there is gonna be C, because remember, at 25 degrees Celsius, it's still a liquid. It's gonna become a gas when it reaches 46. So quite important to remember there. This is a question which is usually asked in grade 10. Now explain why CS2 has a higher boiling point than carbon dioxide. So questions like this are gonna come, whereby now when you are looking at them, CO2 and CS2, what type of intermolecular forces are there in those, right? Both of them, you will see that they are linear molecules, right? This is a linear and this is also a linear, but such that they are non-polar there. You understand? Those are non-polar molecules because you have C bonded to O bonded to C. No, it's CO2. No, sorry. It's the other way around. C, O, and then O, and then CS2 is gonna be S, C, and then S. So both of them are gonna be non-polar, right? Please know that linear molecules, if there are three atoms, then it's gonna be a non-polar. But if there are two, you have to check whether they are the same type of atom, right? If they are the same, they become non-polar, but if they are different, they become polar. You understand? So that's what you must always check out. So for linear molecules. Okay, so these two linear molecules are non-polar, which means in both of them we have London forces. So that's what you must start by saying, is that in CS2 and CO2 there are London forces, right? There are London forces in both. So now, since both of them are belonging to the same type of intermolecular force, how do we compare them? That's when we come to the size of atoms. Now you need to tell us about the size of atom, because the higher the molecular mass, then the larger the molecules, then the more strength that type of intermolecular force will have. So the thing is that when you check them, CO2 has a higher molecular mass. It has a higher molecular mass. When you say molecular mass, remember grade 10 when you're calculating molecular mass. Let's say for CO2, you'd say 12 plus 16 multiplied by 2. 16 times 2, I believe, is 32, and then you're 42, 44, I believe. So it's 44 grams per mole. Then when you check the molar mass of CS2, it's 12 plus S is it 32? Sulfur. What is the molar mass of sulfur? It's how much?
It's 32.
It's 32. Let's see. So it's gonna be 32 times 2. So that would be 64, 74, 76 grams per mole. Ne? Yeah, but the problem when you check that, if we use molecular mass, actually CO2 is going to have a lower molecular mass, which means CO2 was supposed to have a lower boiling point. In this case, it has a higher boiling point. So that tells us that we can't use molecular mass, but that is one of the things you can try. So if molecular mass is not working, you can go to the size of the atoms. When you check the periodic table, as you go down, the size of atoms increase. Okay, the size of the atoms increase. That means chlorine is a bigger atom compared to fluorine. Bromine is a bigger atom compared to chlorine. You see, as you go down, the size increase. And if you check the periodic table, sulfur, I think it's gonna be larger compared to oxygen. Is that true?
Sure.
Hey, so you tell them that sulfur is larger than um, oxygen, hence CS2 will have stronger intermolecular forces. Hence, CS2 is going to have strong intermolecular forces, and because it has strong intermolecular forces, that is the reason why. So more energy will be required to remove. More energy will be required to overcome intermolecular forces. To overcome intermolecular forces in no yeah something wrong with this. um yeah, so that means, yeah, it's gonna be to overcome the intermolecular forces in that CS2. So that's why CS2 will have a higher boiling point. Oh, I was looking at melting point. Yeah, yeah, CS2 has a higher boiling point as compared to CO2. So yeah, CS2 will have a higher boiling point. So your argument number one, you should identify the type of intermolecular force in each molecule there, guided or assisted by the shape of the molecule. Then after that, after you have identified the intermolecular force, then you can come to the strength, right? And then after that, the energy, the conclusion. But then if you find that they have the same type of intermolecular force, you need to then check the size of the atoms that are involved, or you need to check the molecular mass, right? You need to calculate the molecular mass. Yeah. Oh, so it means I think we were also right by just using molecular mass. Just that it's me who was I was looking at melting point for some reason. But even if you use molecular mass, you will see that the molecular mass of CS2, as you saw there, it was higher. I think it's 64 grams per mole, whereas the molecular mass for CO2 was lower, right? So it's either you use molecular mass or you use the size of the atoms. You're the one who's going to choose which one you want to use there. But that is only for molecules that have the same type of intermolecular forces. I repeat, it's only for molecules with the same type of intermolecular forces. So you want to further distinguish between them to say which one has a stronger intermolecular force. You then go to the size or you calculate the molecular mass. Whereas if they have different intermolecular forces, such and then there you can simply go to the list. You go to the list and you compare the strength of those intermolecular forces. You use the list. And then the last question said which one of the substances has the highest vapor pressure. So the one with the highest vapor pressure is going to be the one with the lowest boiling point. You understand? You have to look at boiling point. So when you look at boiling point here, the one with the lowest boiling point is negative is B, ne? It's B. And even if you check in terms of melting point, it has the lowest melting point. So the one with the lowest melting point or lowest boiling point, it's going to have the highest vapor pressure, and vice versa. The one with the highest boiling point and highest melting point, it's going to have the lowest vapor pressure. So in terms of vapor pressure, what we need to remember is that the stronger the intermolecular forces, the higher will be the boiling point, the higher will be the melting point, the lower will be the vapor pressure. The lower will be the vapor pressure. If you can remember that, then you should be fine. Is there any question that from there is anything we didn't understand?
No, sir.
Okay, great. Hope it's the same thing, Miss Candy. If you have a question, now is the platform. But otherwise, that is just about it. You need to just remember your shapes. Very important to remember the shapes, and then in turn knowing which ones gonna have are gonna be polar and non-polar. And just remember your shapes is linear. We have linear. We have bent. But remember, for linear, it could be polar or non-polar. It's gonna be non-polar if it's the same atom that are bonded together, but it will be polar if it's different atoms or if it's three atoms. No, if it's three atoms, it's also gonna be non-polar. But if it's two atoms and then the atoms are different, it's gonna be a polar molecule. And then bent, remember, for bent, all of them they are polar molecules. And then you have trigonal, planar. Trigonal planar is when you have for tri for three. If you have three bonding pairs and zero lone pairs, then it's gonna be trigonal planar. For example, BF3, and then it's gonna be non-polar because it's an ideal shape. And then also gonna have trigonal pyramidal, whereby you have one lone pair and three bond pairs, and that for example NH3, so it's gonna be a polar, this one. And then if you have trigonal um, bipyramidal, that means you have five bonding pairs, and then for example um, five, I believe, so it's gonna be non-polar. And then tetrahedral, also non-polar. Tetrahedral, um, example of tetrahedral could be CH4, they are non-polar, right? Octahedral, non-polar. But the ones that will be polar, right? The ones that are polar, pyramid and some parts of linear. So you can just remember that, you should be okay. Alright, all the best for tomorrow, ladies. Give it your best and just remember these things.